Hello, I wanted to welcome you to IPv6 Fundamentals, a straightforward approach to understanding IPv6. We're going to be doing Chapter 1 this week, which is an introduction to IPv6. Key things that we're talking about this week will be beginning with IPv4, introducing IPv6, the need, and the transition to IPv6. So, let's start with what is IPv4. IPv4 is the Internet Protocol version 4. It was ratified in 1980 under RFC 760. It became obsolete by RFC 791 in 1981. The overall structure of our IPv4 is the header, how it's going to package information. And here's an example of an IPv4 header. It has a version, has type of service, has a length, identification, flags, time to live, the protocol, the source and destination address, padding, checksum, so forth. So there's a lot of information here. A big thing also with IPv4 is it is 32-bit and is represented in 4 groups of 8 digits, or of 8 binary bits, and it looks like this. Here's a group of 8 binary digits that equals 1 octet. Group of 8. So there are 4 groups of 8, and so it should look like this: 10.1.1.1, and each one of those is representation of 8 bits. With 2 to the 32 power, we get roughly 4 billion addresses. Why not more addresses? Because it seems like there's a lot of addresses, but in reality, there really isn't. In IPv4 1981, it was the standard. But realistically, with the world's population at 4.41 billion, we're equal to every address to every person. So that's a 1-to-1 ratio. But we're also talking the internet in 81. That's no internet, no mobile devices, no one's really heard of the internet, no smart devices, no refrigerators, no real smart devices. That's one of the key problems. So most of the times we're dealing with mainframes and mini computers. However, with IBM's introduction to Apple II, the internet started to take off. Things like Yahoo, the World Wide Web, what we think of the internet now, started taking off in the early 90s. That meant everyone was getting on the internet. That meant a rapid, steady growth in the first few years of the early 90s. The EITF, the task force that deals with addressing space, that realized that if IPv4 trends kept the trend going on, would be running out of addresses here very shortly. So that took us to the idea of IPv4 and running out of addresses. Short-term solution included things like network address translation, hiding a private IP address range behind one public IP. That's very common now in most home networks. But that really is not a long-term solution. We've also got the private address space. Any 10-dot network, 192.168 through 172.16 through 172.31, or 192.168 through anything starting with those numbers, all classified as private address spacing. We also got things like CIDR, classless interdomain routing, the CIDR addresses. So that took away our class A, class B, class C, and allowed us to subnet depending on our needs. And that began the start of IPv6. So, what is IPv6? Here's a small header of IPv6. First, you'll notice that there's a lot less dealing with IPv6 in the header. We have the version, traffic class, flow label, payload, next header, hop limit, source and destination. The headers are more simplified. Not a new protocol. It was developed in the late 90s. It learned a lot from IPv4. We changed the bit version from a 32-bit address to 128-bit address space, and we're representing it in hexadecimal now. 2 to the power of 128-bit is 340 undecillion. I might be wrong with my numbering, but it should be 340 undecillion, 282 decillion, 366 nonillion, 920 octillions, sep, sext, quad or quin, then quintillion, trillion, billion, million, 100,000s, thousands, then hundreds. I mean, that's a huge number. So let's see if we can fathom this. That means there is 10 non-million addresses per person. And that's how big a non-million is. That's a huge amount. However, 3 undecillion is the amount of grains of sand on the beaches on our planet. So I mean, that way we can start fathoming how large of a number this is. The internet is a lot different now, and it continues to evolve. Things like mobile devices or smart devices, video on demand, and this thing called the Internet of Everything. A critical part of how we live, work, play, and learn is now directly designed or focused around the internet. IPv6 is not just more about addresses. It has things like stateless auto-configuration so that administrators don't have to create or configure IPv6. End-to-end connectivity, meaning reachability without private addresses, and without NAT, meaning a mobile device communicating globally without the need of masking our addresses. So that means security. That also means things like better support for mobility. That also includes better peer-to-peer networking, because it will be easier to create, maintain networks and network services such as VoIP and QoS, because this is becoming more robust. Things like a small little brief history is kind of important. With 1993, with the ISTF, they called for a white paper for the next generation IPNG. The IETF chose Simple Internet Protocol Plus, written by Steve Dering. You guys can read the names. And that was essentially to change the address size from 64-bit to 128-bit. But IPv4 had a 32-bit address, so where are we getting this 64-bit version? This is actually IPv5, which we'll talk about here shortly. In 95, they actually introduced the RFC 1883, and that dealt with IPv6, and that later was obsolete by RFC 2460, and that was in 1998. So again, what about IPv5? In the 70s, the family of experimental protocols was developed intended to provide QoS for real-time multimedia application, voice and video. Essentially what happened was people didn't get on board, and so IPv5 gone. So this standard was the Stream protocol, or the Stream 2 protocol, RFC 1190 and 1819. Although it was never really known as IPv5, when it was encapsulated, it used protocol version 5, also known as the Streaming Protocol 2. So that was version 5. People didn't get on board with it, it went away. So the need for IPv6. This is an important thing. Why do we need to worry about IPv6? We have 4 billion addresses. Isn't that enough? So that we're running out of addresses. That's a huge thing. These numbers were projected in November of 2014. That means the American ARIN were expected to deplete our addresses in 2015. Latin America, 2014. Most of Asia, already depleted. Most of Europe, already depleted. And Africa by 2019. In January 31st, 2011, IANA allocated the last /8 IPv4 address to the RIRs. What is a RIR? RIRs are regional internet registries. They are the ones that actually lease out names and addresses to the appropriate organizations. ARIN deals with Canada, the Caribbean, North Atlantic Islands, and the US. So that's a big one. The APNIC deals with portions of Asia and portions of Oceania. LACNIC is Latin America and portions of the Caribbean. RIPE, Europe, Middle East, and Central Asia. So Asia actually is covered by RIP and APNIC. Lastly is AFRNIC, and that's Africa and portions of the Indian Ocean. But these regional internet registries are running out of addresses to issue, and that's the problem. They have very few, if any, more IPv4 addresses left to allocate. In America, we still have some. In China, the IP address for a static IPv4 address, they're already run out. There's still some that are there, but they're highly sought after and extremely expensive because they are rare. That's why they are making the move to IPv6. Many ISPs are limited and are running out. So let's look at what the numbers were in June 30 of 2004. We're looking at population based off of people that use the internet and the actual growth. So, North America, we have 353 million people. Compared to Africa and Asia, Asia at its 4 billion plus people, and Africa with its 1.1 billion people. Again, these numbers are from June of 2014, so do keep that in mind. And the internet, actual people on the internet in North America is 87-ish%. Compared to Asia and Africa, Africa at 26% and Asia with 34%. So the actual penetrated population percentage for internet usage for Asia and Africa, fairly low. America, fairly high. However, 34% of 4 billion. We're still looking at over 1 billion people in Asia using the internet. 34% of 4 billion is over 1 billion users still. As compared to North America, with our 350 million and our 87.7%. We're looking at nowhere near the percentage of Asia. So let's talk about this Internet of Everything. The centralized idea in 2010 was the Internet of Everything. That means it wants to have a network of all devices. And there is 12.5 billion devices in 2010. 2015, we're looking at 25 billion. But in the next 5 years, by 2020, we're looking to double that, to have 50 billion devices on the internet. That's going to be several devices per person or per house. Cisco defines the Internet of Things, IoE, as bringing together people, process data, and things to make network connectivity more relevant and valuable than ever before. Things like a smart refrigerator, smart washer, smart dryer, a smart home, smart applications, mobile devices. Those are just a few of the items. Cisco estimated that, again, 50 billion devices by 2020. So now let's talk about no more NAT as we know it, because with IPv4, we had to heavily NAT private addresses. Private addresses are, again, RFC 1918. And part of that was we'd have to hide a private network behind at least one public IPv4 address, which means they were hiding behind one address. It was hard to actually drill down who was doing what when they were hidden. So NAT has been used to hide customers and work from many of the client-initiating applications. The software was not able to track end-to-end devices because of NAT. And that was a problem. NAT also created some issues like peer-to-peer networking and accessing our hidden systems from hidden networks or other networks. Using NAT to hide IPv6 address networks has been the source of some really big debate. IETF, the Internet Task Force, continues to state that NAT is not a security feature. Some of the benefits include better address space. It's now 128-bit. Stateless auto configuration. End-to-end reachability without private networking and without NAT. Better mobility support. And again, better peer-to-peer, which means better network services. The killer applications for the internet is the internet itself. That's the key thing. Lastly, let's talk about the transition to IPv6. So what's involved with this transition to IPv6? And that is actually taking an IPv4 network and putting it on an IPv6 network, or vice versa. So there's things like dual stack. Dual stack runs both IPv4 and IPv6 addresses. These are separate address scopes. So we're not talking IPv4 morphing into IPv6. No. IPv4 and 6 are two separate address schemes. They will coexist for the foreseeable future. Dual stacking allows us to run both. Enterprise and ISPs have to support both protocols, which is one of the reasons why eventually we'll go to IPv6 only, but they still have to support IPv4 for at least a little while. There's this thing called Happy Eyeballs, which is a successor with dual stack hosts. And essentially, you can read the abstract. When a server for IPv4 path and protocols are working, but the server's IPv6 path and protocol are not working, the dual stack client application experiences significant connection delay compared to an IPv6 only client. This is undesirable because it causes the dual stack client to have a worse user experience. With RFC 6535 Happy Eyeballs, success with dual stack hosts. One of the issues that we're going to have with IPv4 and IPv6 is which route? Both? One? The other? Which one? Why? Our book was written by Rick Raziziani, and this happened to be one of his slides. This is going to be, I would imagine, Luigi, his dog. I would imagine, if I'm wrong, I do apologize. But dual stack code may get two addresses back from a DNS. So which one does it use? In order to use applications over IPv6, it's necessary that the user enjoys the same performance, if not better. For example, Happy Eyeballs, success with dual stack hosts. Let's go to Facebook. We query DNS. We get a record, which is an IPv4 IP address, or we query a triple or quad A record for Facebook, which is IPv6. They connect to two different addresses. One is an IPv4, one is an IPv6. We should be able to get our response to Facebook. Let's talk about this in reference to time. The user for Facebook attempts to IPv6 lookup and connection. We're talking about 30 milliseconds for our lookup for IPv4. With IPv6, the retrieval and display may be the same time for first come, first serve. So it's also ultimately going to depend on our operating system and application and the speed of our network. But the initial attempt for IPv6 lookup has seen to be faster. There's also tunneling, which is various protocols to encapsulate IPv6 packets inside of an IPv4 packet network. That way, we can take an IPv6 frame, which is larger, and we can segment it so that we can send it through an IPv4 only tunnel. We also have a NAT64, which translates between IPv4 and IPv6. Native IPv6 is all IPv6 straight across. Our focus and the goal of every organization should be native IPv6. However, not a lot of organizations use IPv6. Learn, use, and familiarize yourself with IPv6. Chapter 2 is going to get heavily into more of the nitty-gritty of IPv6, but you need to start thinking of the importance of and learning and using IPv6 because it's here to stay. So go behind the wheel of IPv6, do test labs for IPv6, implement, test, verify, develop, get plans. However, you're already probably running Windows. You're probably already running IPv6 if you have Windows. But not just Windows. Anything with macOS or Linux is already running IPv6. It's part of that auto state configuration. It's auto doing it for us. But there's already software and applications out there for analyzing IPv6, like packet analyzers like Wireshark. But this does lead to issues like man-in-the-middle attacks. For example, I need a prefix. I need to figure out what my networks are going to be for my IPv6 address. We could have a guy who is going to be our man-in-the-middle attacker. He can set up an IPv6 prefix and gateway and then start responding. He's going to be our rogue RA. He can then respond in between the router and our RS. RA is going to be our router advertisement. Our RS is going to be our router solicitation. So I need a prefix. That's going to be a solicitation. A advertisement is going to be, here's our prefix. And that's one of the bad things because there is no real structure or security within IPv6 as it is. IPv6 by itself is inherently more secure, but because of people not knowing how to configure it, and how to set the network up using it, there are some issues. So that's why you need to learn, use, and transition to IPv6 so that you can deal with more mitigating techniques like RA guard. That way, we can take that basic insecurity because of engineers not knowing how to use it and put a guard in front of it. So get familiar with IPv6. That's actually it for our Chapter 1 for IPv6 Fundamentals. I wanted to thank you guys and hope you have a great day.